Welcome back to the deep dive. We take the densest research, the latest articles, and we pull out the insights you need for those real aha moments. Today, we are tackling it's got to be one of the biggest scientific engineering challenges out there, achieving sustained, controlled nuclear fusion.
It's a huge one. It's often called, putting a star in a jar. And our mission today is to get past the basics of how fusion works and really focus on the main technical hurdle. It's not really about getting the plasma hot anymore. We're pretty good at that. The real problem is, it's managing the chaotic, unbelievably unruly nature of that plasma once you've got it.
Right, and that struggle has led to this really revolutionary shift in thinking. And we're moving away from what you could call a brute force method.
Yeah.
Kind of waiting for the storm to hit and then trying to stop it with a giant punch.
Exactly, and moving to a totally new model, an approach that tries to find the plasma's natural heartbeat, its rhythm, and then, keep it calm before an instability can even start.
So this insight is coming from cutting-edge research, sources covering major labs like Princeton and the DI facility.
That's right, and to really get the stakes, we have to understand the setup. This all happens in tokamaks, these huge donut-shaped machines. We're talking about confining plasma heated to over 100 million degrees Celsius.
Which is hotter than the core of the sun.
Many times hotter, and it's all held in place by these immensely powerful magnetic fields.
Those fields are what create the star in a jar, keeping the plasma from just melting the reactor walls.
Precisely. But the goal isn't just one quick flash of energy. For a power plant, you need what's called a sustained stable pulse, a reaction that can last for minutes or even hours, and that just requires absolute control.
Okay, so let's unpack that. Why is it so chaotic? Because when you see the diagrams, the plasma always looks like this perfect glowing donut.
Yeah, those diagrams are, let's say, optimistic. Almost immediately after you form the plasma, that smooth surface starts to develop these really severe instabilities.
So that's where the chaos begins.
It is. Picture a super heavy, super pressurized fluid that is desperately trying to escape. It starts kinking, forming loops, wrinkling up. And the unique thing about plasma is that any tiny ripple in the magnetic field just accelerates that chaos. A small wave becomes a catastrophic one.
So we're literally trying to tame a controlled storm inside a box.
That's a perfect way to put it.
The sources really focus on two main threats, two instabilities that we have to worry about. What are they?
Okay, so the first, and maybe the more common one, happens right at the edge of the plasma. They're called edge localized modes, or ELMs.
ELMs.
Yeah, if you could see them, they'd look like little solar flares erupting outwards from the surface.
I found this part a bit confusing. The sources seem to say that scientists sometimes actually want ELMs to happen. Why would you want these energy bursts?
Yeah.
That sounds like you're just accepting damage.
That's a really sharp question. And it gets to a classic fusion paradox. See, ELMs tend to happen when the plasma is in its most efficient state, something called H mode, or high confinement mode. And while a really big ELM is definitely damaging, these smaller repetitive bursts actually do something vital. They act like a cleaning mechanism. They purge impurities from the core, things that would otherwise build up and poison the reaction.
So it's a necessary evil. You have to manage it, not eliminate it.
Exactly. We have to live with them, but we have to control their size. A single large ELM is terrifying. It can expel up to 20% of the reactor's total energy in one shot.
20%.
All of it crashing right into the diverter plates, the components meant to exhaust heat. That kind of focused energy blast can just destroy the wall materials over time.
Okay, so if ELMs are the solar flares, what's the real catastrophe, the thing that keeps engineers up at night?
That would be the full disruption. A disruption is when an instability, often starting small, just grows uncontrollably and leads to the rapid total collapse of the plasma.
So the whole thing just goes out.
It goes out and you get a massive sudden loss of energy. But the real danger is what happens next with the magnetic field.
What happens?
As that field collapses, it acts like a giant transformer. The sudden change in flux can accelerate any stray electrons left in the chamber to nearly the speed of light. They become runaway electrons.
Wait, so you're telling me the tokamak accidentally turns into a particle accelerator?
Unfortunately, yes. And these runaway electrons have enormous energy. If that beam hits the reactor's inner wall, it can literally melt the interior surfaces. This is the absolute catastrophic failure scenario.
Wow. Okay, that brings us right to the old playbook then. The brute force method. It sounds like all the traditional approaches were just about damage control.
That's been the framework for decades. An instability starts, you hit it. hard and fast. For the ELMs, the goal is basically to replace one giant damaging burst with a whole lot of smaller, harmless ripples.
So how do you physically do that? How do you hit a plasma that's hotter than the sun?
You use some really impressive hardware. The first technique is called resonant magnetic perturbation, or RMP. They have these special coils inside the vacuum vessel, and they use them to create a small, slightly distorted magnetic field.
So they're deliberately making the magnetic cage a little bit leaky, a little bit imperfect.
That's a great way to think about it. They introduce a tiny wrinkle, and that subtle change alters the paths of the particles at the edge, making it easier for them to escape. It basically forces the plasma to constantly shed a little bit of energy in tiny bursts, instead of saving it all up for one big one.
Like breaking one big tidal wave into a bunch of small ripples.
That's the idea.
And what's the other method, the second brute force technique?
That would be pellet injection. They literally fire tiny pellets of frozen fuel, usually deuterium, right into the edge of the plasma at incredible speeds.
Firing ice cubes into a 100 million degree plasma. That sounds intense.
It's an amazing engineering challenge. They use gas guns to launch them at hundreds of meters per second. And the physical shock of that pellet hitting the plasma edge does the same thing. It triggers smaller, more frequent energy releases.
So we've covered managing the ELMs, but for the real crisis, the disruption, the sources say you need an impossible amount of speed.
You need extreme speed, and because of that, you need extreme force. You're in a full-blown crisis. To stop that runaway electron beam before it melts a hole in your multi-billion-dollar machine, you have to act in less than 5 milliseconds.
5 milliseconds. Just for context, a blink of an eye is maybe 300 milliseconds.
Yeah.
We're talking about a time window that is almost instantaneous.
It is. And since there's no time for subtlety, the solution is just massive physical impact. They inject huge pellets, some bigger than a wine cork, made of frozen deuterium and neon, straight into the chamber.
These are not the little pellets you mentioned before.
No, these are huge. And the engineering challenge is that they have to be shattered into a cloud of fragments right before they hit the plasma. If they don't shatter, the plasma can't absorb them fast enough, and it's too late. It's a true crisis response.
Okay, that really sets the stage. Decades of engineering built around a 5 millisecond panic button.
That's a good summary of the state of the art in taming that storm.
And this is where it gets really interesting. Because instead of reacting, the new breakthroughs are all about prediction, about listening for the plasma's internal heartbeat, its rhythm, and keeping it calm before the storm even starts.
This is the revolutionary part. Prediction just changes the whole game. The research focused on what are called tearing mode instabilities, which are a major cause of those full disruptions we were just talking about.
Tearing modes, where the magnetic field lines literally just rip apart.
They break and reconnect, yeah. It lets the plasma leak out very, very quickly.
So how on earth do you teach a computer to listen for something like that?
They use something called deep reinforcement learning, or DRL. It's a type of AI that learns through trial and error, getting rewards and punishments. Researchers fed this AI just a massive amount of experimental data from the DID tokamak.
You had an analogy for this, like a pilot trainee.
Yes, think of the AI as a pilot in an incredibly complex flight simulator. The simulator is the plasma. The reward is maintaining high fusion power. And the punishment. The punishment is triggering a tearing mode instability.
So the AI is just running millions of these simulated flights, learning that, oh, if these 3 variables line up just so, a crash is coming, and it gets a negative point.
Exactly. And over millions of trials, it doesn't just learn what not to do. It learns the optimal path forward. It maps out the subtle, stable rhythm, the plasma's heartbeat, that keeps performance high while staying far away from the edge of that cliff.
Okay, so what was the time gain? Because going from 5 milliseconds to anything more is a huge win.
It's incredible. The AI could predict a potential instability up to 300 milliseconds in advance.
300, that's not just a win, that's a different sport entirely.
It's a lifetime in fusion control. We're talking about going from a panic button to genuine proactive control.
So with that 300 millisecond head start, what does the AI actually do? It doesn't need to fire those giant ice corks anymore, right?
No, because it acts before the crisis even begins. The AI becomes the controller. It uses that window to subtly change the operating parameters. It might tweak the shape of the plasma or adjust the power of the heating beams.
So it's adjusting the rhythm. It's calming the plasma down before it even knows it's having a bad day.
That is the perfect way to put it. It makes these small, calculated changes that steer the plasma away from the conditions that cause the instability in the first place. It's the difference between mitigation and active, predictive prevention.
And I thought it was really interesting that humans are still in the loop. The AI isn't just running the whole show by itself.
Not at all. The human researchers are essential. They act as arbiters. Sometimes the AI will suggest a change that's correct in terms of physics, but it's just too fast for the physical hardware, the magnets, the power supplies to actually execute safely.
So the humans are there to smooth things out.
Exactly, to make sure the AI's commands are practical for the machine, preventing the solution from causing a new mechanical problem.
So connecting this to the bigger picture, what does this all mean? Is finding the plasma's heartbeat the key to finally getting sustained fusion power?
I think it provides the essential foundation for it. This predictive approach gives us a blueprint for solving a whole range of plasma instabilities, not just tearing modes. It directly addresses that core problem of chaos, which is what's been holding us back from achieving those long, stable pulses you need for a power plant.
And it seems like the AI is doing more than just controlling. It's also teaching the physicists.
That might be the most profound part of this. The researchers found that by studying the AI's decisions, they're learning new things about plasma physics. The AI finds solutions and pathways that are sometimes radically different from what traditional physics would suggest.
So it's finding strategies a human might never have even thought to try.
Yes. So it's not just a tool for control, it's becoming a tool for discovery.
That raises a big question then. What really stands out to you here? We have this amazing proof of concept for one instability. What's the next big hurdle to clear?
I think the next hurdle is integration at scale. This AI learned to control one specific problem. The next generation of these systems will need to handle multiple instability types, ELMs, tearing modes, and others all at the same time, without their control actions interfering with each other. It has to conduct the entire orchestra, not just play one instrument.
That's a powerful thought to leave you with. The idea that the technology we're building to control nature might end up teaching us new fundamental truths about how nature actually works. We built a pilot for our star in a jar, and now it's showing us flight paths we never even imagined.
And this deep dive, centered on the idea of the fusion heartbeat and that shift from brute force to predictive rhythm, was brought to you by the insights curated by Vario1.
If you enjoyed uncovering these breakthroughs in plasma control, we really encourage you to check out more synthesized insights like this on the Vario1 website. Join us next time for another deep dive.